Hello, it's Keith here, and this is the first in my TMS9900 assembly programming tutorials. Now I know what you're probably thinking, what the heck is the TMS9900, why are you covering it, and why the hell should I be interested? Well, the answer to that is the TMS9900 was an early server processor like the PDP-11. It was later used as a desktop processor in the TI-99 computers. Those weren't calculators, those were desktop computers like the 994A. And why I'm covering it, well, after doing the PDP-11, I became quite interested in looking at these old processors because there's often things to learn from them because of how they do things differently to the processors we're more used to, and also in some ways how they do things the same. I thought it was quite interesting to see the sort of roots and to see the different ways things have been going on. So that's why I've covered them, and hopefully that's why you might be interested in them. Now, the main thing that I find so curious about this CPU is that, unlike, to my knowledge, every other CPU, at least every other one I've come across, the TMS doesn't have a stack, which if you know other CPUs is going to be a bit baffling because the stack is of course used for subroutines and things. So we're going to have to learn how we work around that. The other thing about the TMS9900 is it only has very, very few registers. It's very much like the 6502 in that only has about 3 registers. And again, this is going to mean some quite different ways of working with things. So I find it really quite a curious missing link, if you will, where it kind of fits in between the sort of ARM type processors, which use link registers for jumps and things, and it fits in between the 6502, which has a stack but has a 0 page, and systems like the Z80, which has a stack and a lot of registers. It really has a lot of different ideas in there, and I think it's quite curious to learn about this CPU, even if you're not maybe very interested in actually writing code for it, although we will be learning how to, of course. I think it's really quite fascinating. So we're going to have a look at it today. We're going to be learning about some code, and as usual, you can go to my website, get a cheat sheet, download some pre-configured scripts to build your own code and test it, whatever you want to do. So let's go over the theory first, and let's have a look at those registers and learn about the system. Now, in this tutorial, I'm going to assume you've got at least a basic knowledge of, how hexadecimal works and binary and things, because this would be a very strange choice to go for if you've really never programmed assembly before, if you don't understand those kind of things. Although, of course, I guess there's maybe a few TI-99 fans out there, which case, welcome. I hope you enjoy these. But I'm going to assume you've got some vague understanding of it. Now, the assembler we're going to be using is macro assembler. Now, this doesn't actually use the classic syntax. The classic TI-99 assembler used a greater than symbol at the start of a value to represent hexadecimal, which is very strange if you're used to 6502. The assembler we're using doesn't use that. It uses more traditional Intel syntax, so a 0 at the start. It's got to start with a digit, not a letter, and a H at the end, or B at the end for binary. So that's just something you might have to sort of come across. It's just the way this one works. If you're used to another one, or if you're using other source code, you may need to make a few changes. But because I work on so many different platforms in my tutorials, I try and use as few assemblers as possible. And in this case, the syntax isn't really that strict, to be honest. So we're just going to have to accept that. Now, the TMS9900 is a big endian machine. Little endian is, of course, where you store the lowest byte first and then the high byte second in a 16-bit pair. All of the registers on the TMS9900 are 16 bits. Now, there are byte commands, rather strangely compared to other systems where a byte command will use the low half of the register. The byte commands on the TMS9900 use the high byte of the registers. So if you think of the two pairs, this is the low byte that would be used by most systems for the byte commands, like the 68000, for example. It's this byte, the top half, that was used. We'll see that later on, though. It's just something that really caught me out. So how do the registers work on the TMS9900? Well, we've got 3 basic registers. There's the program counter, which, as in all of the systems, is the current running byte of code. This is where the processor is executing from. There's something known as the workspace pointer, and this is really the key to how it copes with so few registers. Now, the workspace pointer points to a 32-byte area of memory, and this is essentially used a bit like a 16-byte 0 page or direct page, depending on the CPU you're familiar with in the 6502 type series. And basically, this will define what are known as workspace registers. Each of these is 16 bits using 2 bytes, and these are effectively the variables we use for our storage, and they're sort of treated as registers. They're called registers in the documentation, but on the 6502, they're effectively the same as the 0 page. And so this is our area we use for our working data. And when we want to run a subroutine, one of these registers is used as a link address, R11 typically. So that will be the return address that the execution needs to continue from when the subroutine finishes. But in the case that a subroutine needs to use a lot of registers and we need to back up those somehow, what we do is we actually start a new workspace, allocate a new area of memory for a new 16 registers with 32 bytes total data. And that is how we get around the fact that we have so few real registers, and how we've got no stack, and how we deal with subroutines and backing up values. So we'll be looking at all of that much later in a later lesson, not today. Today's just going to be simple, but I just wanted to give a brief introduction to the concept of the workspace registers, the true registers, and we've of course got a status register, and this is just for flags, and we'll be looking at that again in a later one. So we've got 3 true registers, 16 workspace registers, and that's really all we need to worry about. So in lesson 1, as with our other series, we're going to be going over the real basics. We're going to look at a very simple example, which you can download from my website. And then we're going to look at how to load some values into registers and just shuffle them around a bit, just for some getting started fun. Let's go to the source code and have a look. Okay, so first of all, let's have a go with this minimal example. Now, in this series, I can't call it a multi-platform series. It would be a lie because we're only covering a single platform. This is really, unlike my other series, this is going to be very much a fire and forget. We're going to do a bunch of tutorials on it, and then we're just going to leave it and move on because I'm covering too many series at the moment already. I think this is fascinating, but I can't really take it very far because so few systems use this CPU. But anyway, we've got a header, which will get us a program started fairly well. We've got a footer here with some functions that we're going to include, are going to help us out here, and these mimic my other systems. Now, in other platforms, we'd have the ability to compile to multiple destination systems, but as I say, in this case, I'm afraid I don't have that, but we do have at least the ability to compile for the TI-99. So let's just fire up this emulator just here. Okay, so here we go. Here's our emulator here, and if I just press 2 here and then 2 again to start the cartridge, and you can see we've got a simple hello world example here. We're showing a 255 terminated hello world message. I always use 255 termination in my examples. A few new line commands here. We're dumping the workspace registers here. You can see them all just here, and you can also see the workspace pointer, program counter, and the status register here. So we've got a dump of all of the settings, and then here we've just dumped a little bit of memory to the screen as well. So this is a sort of template, if you will. Now, if you wanted to write your own program, you would just replace this bit here with whatever you actually wanted to use. Now, like with most assemblers and like most assembly languages, you can see we've got labels here on the left with a colon at the end. We've got a jump to a label here, so this is using, the assembler is converting this label to a byte of the resulting code here. And BL is for branch and link. This is running a subroutine, and this is actually a label within the functions. And you can see there's an @ symbol at the start of this to define it as an address here. Here we're loading an address as an immediate here. You can see this hello world here. This is being loaded into register 1, workspace register 1 that is. We're going to have a look at all this in a moment here. And here we're loading a hexadecimal address into R5. So we're going to go over all of this in just a moment. At the bottom here, you can see we're defining a byte. We're defining a sequence of bytes here. Actually, it's a string and a single byte here. And here we're aligning to make sure we're even aligned. This is a 16-bit processor, despite its limited functionality, relatively speaking, like the PDP-11, it is 16-bit. So we need to be even aligned at all times. Okay. Now, assembly, we're just going to go over this very quickly. As again, I recommend you download my example code and my scripts so you can compile these yourself. But you can see we're using ASW here to assemble. We are compiling for the CPU TMS9900, outputting a build file and then converting that to a binary and running that as a ROM file, a cartridge, on the classic 99 emulator here. Now, the header is, of course, in here, so this is doing a lot of the work for you. We're not going to cover that in any more detail. We're going to do that in a later hello world example. So for today, as I say, I'm recommending, if you are interested in running this, just go ahead and get the scripts, and hopefully you should be able to run these on your home machine. Okay, so let's move on to the first example we're actually going to look at today. This is lesson 1. So in lesson 1, we're just going to do a little bit of simple work with the registers. So we're going to start with this move load example here. You can see we're jumping straight here. Our first command here is just branch and link to a subroutine called screen init, which turns the screen on and sets the colors. You see there's an @ symbol here to represent that it's an address to jump to. If we just run this, and here it comes. So if I just press 2 and 2 again to start our system up, there we go. So let's just get this on the top and let's have a look at what's actually happened here. So our first command we're going to learn today is li. This is load immediate. So what this is doing is it's loading the immediate value on the right, 1, 2, 3, 4, into the register on the left, R0. And this is of course a decimal value here. So this has actually been sort of converted here. You can see R0 here is actually 04D2. If I get my calculator up here, 1, 2, 3, 4, oh, 1, 2, 3, 4, and then I press hex, 04D2, you can see that's worked just fine. So that's the hexadecimal representation of the decimal we specified here. Next, we're doing the same with R1. You can see our first execution of the monitor command, which shows these results, is down here. So you can see this is the result of all 4 of these commands just here. So we've loaded 1, 2, 3, 4H. This is in hexadecimal, and you can see that is just there. Now this needs to start with a digit, so if this was F234, we'd need to put a 0, but if it's 1, 2, 3, 4, we don't need to, but I've just put it in there for completeness. So that's how we use hexadecimal. As I say, if you're using a classic 99 assembler or you're reading the old manuals, you might see this greater than symbol, and that is actually hexadecimal on those old assemblers. Now, I say that's quite baffling to me because I'm used to the 6502 where that's the greater than and takes the top byte, but that's the way the assemblers used to work, but it's not the way this assembler works. This assembler is using the Intel style. Now, in the case of binary, it's also using the Intel style, a B at the end. So this is a binary value, and you can see that's been converted to F9 here. And then we also can do octal with an O at the end, and 377 in octal is 255, which is FF in hexadecimal. So you can see here, we can use all of these bases very easily just with a suffix and a 0 as prefix if needed. So there we go, that's how we can do that. And the load immediate command, source on the right, destination on the left, and the source is always a fixed value and the destination is always a register, a workspace register. Okay, so that's how we can load in values into our registers. Now, as well as that, we do have the option to use ASCII. So you can see that here, we're loading in some ASCII values. So we're loading into R0 here, an A and a space. Now, you can see here we've loaded various values, and this one is kind of just a byte value here, FF, but actually we're loading in 16 bits each time here. So in this case, we're making that very clear just by specifying 2 letters here, because of course 1 letter is 1 byte, and so 2 letters is 2 bytes, 16 bits. So here we're loading a space, and you can see 41 is the letter A, and 20 is the space. This time we've only specified a single byte, and it's been loaded in down here, and the top byte is 00. And here we've specified 2 A's, 4141. Here we've specified 2 spaces, 2020. So you can see here we can specify up to 2 letters if we want in this way. Now, one important thing to remember, as I said before, is that when we do byte commands, only the top part of the register will be used. It's the single top part that's used as the byte, not the bottom part like on other processors. So if you're using the print char command, which is in my functions, you would actually need to load the pair in this way if you wanted to show an A, because you need the character you're going to show to be in the top part there. So that's just something that, as I say, we'll come across it in a moment. Okay, so we've loaded in a variety of values into registers here. Now what we're going to do is we're going to move between registers. So first of all, we're going to move from R0 to R1. Now, unfortunately, as is the case in a few other systems, the immediate syntax is source on the right, destination on the left. With the move command, it's the other way around. The source is on the left, the destination's on the right. So this command is saying load A into R1 is an immediate, and this one is saying move the value in R0 into R1. So you can see here, R0 used to be 4121 and R1 used to be 0041, but R0 has been moved into R1 here. So yeah, that's what's happened there. Now next, we've done the same just to confirm that, moving R0 into R2, and you can see R2 has now been filled with 4120 as well. So all 3 of these now are 4120. And then we do that again here, and now all of them are 4120. Okay, so that's how we can move values between registers and how we can set registers from immediates. There are a couple of special commands. If we want to set a value to 0, we could of course load immediate 0, but the size of these commands is quite big, so we might not want to do that. These are 16-bit commands and these are 16-bit immediates, so we're using quite a lot of memory here. So we can save some memory by doing a single command here, clear R0, and that will set a register to 0. So that will save us a pair of bytes there because of not having to specify the immediate. We can also set all the bits to 1 here. Set O, set 1s, R1 here. That will set to FFFF here. So those are some options for us if we have more specific requirements and we need to save a little bit of memory. Okay, so let's move on now to a little bit of simple mathematics. We're going to do some adds and subtractions here. So let's fire up this example here. And let's just fix that onto the top here. Okay, so here we're loading all of the registers with 1, 2, 3, 4 here. You can see that just here. And then we're going to do some adding and subtracting of immediate values. Now, LI stands for load immediate. AI stands for add immediate. It's not artificial intelligence, funnily enough. Okay, so here we're going to add the immediate value of 4 to R2 here. So you can see R2 used to be 1, 2, 3, 4. We've added immediate value 4 to R2, the destination on the left again, and that's become 1, 2, 3, 8. Now, logically speaking, you'd think there was an SI, subtract immediate, but there isn't. However, the good thing is we can specify a negative immediate. So we can add -4 to R3, and that does the same thing as subtract immediate, but SI doesn't exist. So anyway, so you can see here we've taken 1, 2, 3, 4 in R3. We've subtracted 4, or added -4 if you prefer, and that's become 1, 2, 3, 0. So that's how we can do that. Now, as well as working with immediates, we can of course use a pair of registers. So one register is our destination and the other register is the parameter to add or subtract from that destination. Again, like the move command, in this case the source parameter is on the left and the destination is on the right. So again, the opposite of the immediate commands. So here we're loading R1 with 10 hexadecimal, which is 16, and then we are adding, A stands for add, the 16 hexadecimal 10 to R2, and you can see here that R2 has gone from 1238 to 1248 because 10 has been added, and we subtracted that hexadecimal 10 from R3, and you can see this went from 1230 to 1220. So adding and subtracting, source on the left, destination on the right, adding immediates, destination on the left, source on the right, or parameter on the right maybe would be the better way of terming it. But anyway, that's the way it does it. I get a little bit confused about this myself, so please go onto the website and get that cheat sheet to just double check things if you're struggling a bit with the syntax of these commands. Okay, so that's addition and subtraction. Let's move on to a few more little commands that are going to finish this lesson off for us. Okay, so we've looked at addition and subtraction of immediates and also register values. Like most systems though, we're going to want to do incrementing and decrementing, increasing by 1 and decreasing by 1. We of course have increment and decrement commands, but unlike most systems we have quite a nice little command here. We have inct and dect, and this increments by 2 and decrements by 2. So I guess this is for reading in 16-bit values. You don't want to move by 1 byte, you want to move by 2 bytes, and we've got special commands to do that. So they're just the exact same as a normal inc and dec command, so we just specify a single register. And again, unlike the immediate addition and subtraction, these are a single 16-bit command, whereas these are 16-bit commands with a parameter. So these are smaller commands, so these would be what you would want to try and use. Okay, so you can see here we started off with 1, 2, 3, 4 in all the registers. We then incremented R0, so that went from 1, 2, 3, 4 to 1, 2, 3, 5. We incremented R1 by 2, inct, so that went from 1, 2, 3, 4 to 1, 2, 3, 6. We then did a decrement of R2, so that went from 1, 2, 3, 4 to 1, 2, 3, 3. And we did a decrement of 2 from R3, which went from 1, 2, 3, 4 to 1, 2, 3, 2. So it went down by 2, of course. And you can see we've just repeatedly done the same commands over and over here. So you can see each time this one's gone down by 2, this one's gone down by 1, this one's gone up by 2, and this one's gone up by 1. I suppose I could have put a loop in here, but I've just copied a lot of commands there. But anyway, you can see there, we've got a few simple mathematics commands. Okay, well, that's actually all we're going to cover for today's lesson. This was just a brief introduction to the processor and a simple bit of mathematics on it. We're going to be continuing. I've got quite a few lessons planned for this system because I find it quite fascinating, and I hope you will as well. So next time we're going to be looking at the addressing modes, the memory reading and writing options. And so hopefully, if you're interested, you'll join me for that. If you have, please like and subscribe so you catch my other content. If this is a little bit too weird for you, I totally understand that. Please check out my other videos. I've got lots of tutorials on other systems. I've got much more classic stuff like Z80, the 68000, modern stuff like the ARM, and we're going to be doing RISC-V soon. So please check out for that. I've got a Discord and a forum if you want to chat about assembly programming and things. So, if those are the kind of thing you're into, please check out those. But whatever you do though, I hope you'll find something you enjoy programming, and I hope you enjoy assembly language. Thanks for watching today, and goodbye.